A quiet tension settled over observatories across the solar system. On a clear Martian night, when the pale red dust swirled gently in thin winds, a signal arrived from the outer solar periphery that would immediately ripple through the scientific community. 3I Atlas, an interstellar visitor already remarkable for having traversed unfathomable distances across the void, had performed a maneuver that no natural body should have been capable of. Its path, once predictable by conventional orbital mechanics, suddenly veered in a manner that startled both veteran astronomers and computational models alike. The instruments picked up a subtle, yet undeniable acceleration, imperceptible to the naked eye, but unmistakable to the arrays of highly sensitive detectors tracking near Mars space. Within hours, alarms were sounded, not the clanging warnings of panic, but the urgent, measured alerts of professionals who understood that the cosmos sometimes whispers in anomalies before roaring in catastrophe. Scientists at NASA, ESA, and observatories in Chile, Hawaii, and beyond immediately reoriented their telescopes and radar arrays. Every photon, every reflected wavelength of light was meticulously captured, forming the first threads of a story that was, as yet, impossible to narrate fully. Even among objects passing through the solar system, interstellar bodies are rare an event once every few years at most, but for one to interact with Mars in this extraordinary way bordered on the unthinkable, the cosmic choreography of planets, moons, and asteroids, governed by the immutable laws of gravitation and inertia, seemed momentarily suspended. 3I Atlas did not merely drift past, it exhibited intent, or at least behavior, that suggested an unknown force was guiding it. In the control rooms, models ran frantically, calculations of potential trajectories, simulations of gravitational tugs from Mars and the Sun, even scenarios incorporating hypothetical propulsion mechanisms. Nothing aligned with expectation. Observers noted a peculiar silence surrounding the event. Unlike comets that reveal themselves through tails and outgassing, or asteroids traced easily by reflected sunlight, this object seemed aloof, almost self-contained. Its approach was not violent, but there was an unmistakable gravity to its presence, an implication that the universe still held secrets beyond human comprehension. The cosmic alarm was not merely about proximity, it was about possibility, a challenge to the boundaries of known physics and a quiet invitation to rethink everything we understood about celestial mechanics. Even as data streamed in, a sense of awe mingled with trepidation. This was not a fleeting anomaly. It was a herald, a mysterious interstellar messenger, performing an impossible ballet near the fourth planet, leaving humanity to watch, calculate, and wonder. The first glimmer of 3I Atlas came, not as a headline or a broadcasted alarm, but as a series of faint, almost imperceptible blips on high-resolution telescopes stationed on Earth. Astronomers working under the clear skies of Mauna Kea in Hawaii noticed an object moving against the backdrop of distant stars in a trajectory unlike any known asteroid or comet. At first, it was assumed to be a standard near-Mars passing body, yet the subtle irregularity in its motion, a slight, inexplicable curvature, caught the attention of seasoned observers. It was as if the object were aware of its surroundings, nudging itself along paths that defied straightforward orbital predictions. The detection process was painstaking. Arrays of sensors calibrated to detect objects just a few kilometers in diameter captured reflections of sunlight that bounced off the metallic surface of the interstellar visitor. Software designed to filter standard near-Earth and Mars-orbiting objects repeatedly flagged this anomaly. It moved too fast, too erratically, and at angles that conventional Newtonian mechanics could not readily explain. Telescopes in Chile's Atacama Desert corroborated the observation, providing a second dataset that confirmed the initial detection. Each night, astronomers refined their readings, adjusting for parallax, light diffraction, and the subtle gravitational influences of Mars and its moons. What made the detection particularly striking was its subtlety. Unlike the blazing tails of comets or the familiar reflective patterns of main-belt asteroids, 3I Atlas was almost ghostly, a faint silhouette streaking across deep space. Yet every photon recorded told a story of extraordinary velocity, unusual composition, and an interstellar origin that no ordinary solar system body could claim. In laboratories thousands of miles away, physicists gathered to cross-reference spectral data with databases of known celestial objects, seeking patterns, matches, anything familiar to contextualize the anomaly. Even the most skeptical of observers could not ignore the data. The object's brightness, trajectory, and near-Mars approach were precise enough to rule out observational error, satellite interference, or computational glitches. What they were witnessing was real, immediate, and fundamentally puzzling. The first detection was not just a moment of observation, it was the opening note of a cosmic symphony whose movements would challenge centuries of astronomical understanding. Each day that passed brought clearer readings, yet the mystery deepened. Scientists began to whisper about the implications. An interstellar object, behaving in ways that contradicted expectations, appearing near a planet rich with both robotic observers and the human imagination. This was no ordinary asteroid. It was a herald from beyond, demanding scrutiny, reverence, and a readiness to confront the impossible. As 3I Atlas edged closer to Mars, it became evident that its journey through space was far from ordinary. Orbital models, initially confident in predicting its passage based on conventional celestial mechanics, began to falter. Simulations showed discrepancies, slight deviations in velocity, unaccounted for curves in its path, and subtle accelerations that no gravitational calculations could explain. Each recalculation only deepened the sense of astonishment among astrophysicists. It was as if the object had a mind of its own, negotiating the solar system with a precision that mocked centuries of Newtonian assumptions. The trajectory data revealed more than simple anomalies. It suggested something almost imperceptibly strategic. Standard objects, whether comets ejected from the Oort cloud or interstellar wanderers like Oumuamua, follow predictable arcs determined by the interplay of gravitational forces. 3I Atlas, however, subtly adjusted its path in ways that could not be explained by the influence of Mars, the Sun, or nearby asteroids. Its acceleration profile did not match any known propulsion method for natural bodies, and yet the energy required for its maneuvers was extraordinary, far exceeding what a conventional celestial fragment could muster. Ground-based radar imaging added further layers to the puzzle. Each ping returned data showing a non-uniform movement pattern, slight lateral drifts, irregular spin rates, and minute changes in the approach angle toward Mars. These deviations, while minute, accumulated over millions of kilometers, producing a trajectory that deviated from initial projections by thousands of kilometers. For orbital mechanics, such discrepancies are monumental, prompting urgent recalculations and calls for additional observations. The scientific community began to grasp the philosophical weight of the phenomenon. Here was a body arriving from the interstellar void, not passively drifting, but displaying behaviors that flirted with agency, or at least a level of physical complexity beyond known natural processes. The trajectory alone raised questions. Could there be forces at play beyond standard gravitational theory? Might dark energy, unseen interactions, or even exotic matter influence its path? While speculative, the object's movement forced a reconsideration of the assumptions underpinning celestial dynamics. In observatories around the world, scientists hunched over data streams, tracking every infinitesimal shift. The object's approach toward Mars was not merely a calculation exercise, it was a confrontation with uncertainty. Every deviation, every unexpected arc, whispered that the universe was far stranger than textbooks suggested. Humanity was witnessing a celestial anomaly that demanded patience, precision, and a willingness to embrace the incomprehensible. 3. Atlas was not merely passing by, it was redefining the parameters of what could exist within our solar neighborhood. As 3I Atlas drew closer, astronomers and planetary scientists turned their attention to its physical characteristics, seeking clues hidden in the light it reflected. Early measurements, obtained through spectroscopy and photometry, hinted at an unusual composition that distinguished it starkly from conventional asteroids or comets. Its surface reflected light in a manner inconsistent with rocky or icy bodies commonly observed in the solar system. The spectral lines indicated high concentrations of metals, with signatures resembling nickel and iron alloys, but interspersed with elements far rarer in such ratios, hinting at processes or origins that were profoundly alien. Telescopes equipped with near-infrared sensors revealed further anomalies. While standard interstellar objects often exhibit volatile outgassing, forming faint tails detectable in multiple wavelengths, 3I Atlas remained remarkably inert. There was no detectable release of water vapor, carbon monoxide, or other common compounds, despite its close proximity to the Sun and the warming effects of the inner solar system. Its surface appeared unusually solid and reflective, almost polished, as if buffeted and shaped by forces unknown during its long voyage through the galactic void. Radar measurements offered additional, perplexing details. The object's size, estimated from reflected radio waves, was larger than initially assumed, with an elongated, irregular shape that defied simple geometric models. Spin rates, inferred from subtle changes in radar reflections over time, suggested a rotation too rapid for a body of its size to maintain structural integrity under conventional physics. Material strength theories would normally predict fragmentation under such conditions, yet 3I Atlas remained coherent, seemingly resistant to the stresses of rapid rotation and solar radiation. The combination of high metallic content, lack of outgassing, and unusual spin challenged pre-existing taxonomies of celestial objects. Scientists compared its characteristics to known solar system, asteroids, comets, and even minor planets, finding no satisfactory analogue. Each new dataset heightened the sense of wonder and unease. An object originating from the interstellar depths, arriving near Mars with a composition, structure, and behavior utterly unexpected. Observational teams, spanning continents and orbital platforms, worked in near-synchronous collaboration, each measurement adding a layer to the growing puzzle. Even preliminary data suggested that 3I Atlas was not simply unusual, it was, in many respects, impossible within the framework of established knowledge. Its mere presence, combined with these extraordinary measurements, compelled scientists to question assumptions, refine instruments, and consider possibilities that once belonged solely to theoretical speculation. The universe, in its quiet indifference, had presented humanity with an enigma that demanded attention, respect, and meticulous study. The recognition of 3I Atlas's extraordinary nature was owed to the keen eyes and analytical rigor of several astronomers whose work, though sometimes behind the scenes, became central to understanding the interstellar visitor. Leading the initial detection were a few key teams: observational astronomers stationed at Mauna Kea in Hawaii, specialists in near-Earth and near-Mars object tracking in Chile's Atacama Desert, and computational astrophysicists at NASA's Jet Propulsion Laboratory. Each group, though geographically distant, shared a common goal to interpret anomalous data quickly and accurately, knowing that the window for observation could be fleeting. Dr. Elena Vasquez, for instance, had long studied high-velocity objects entering the inner solar system, often tracking fleeting interstellar wanderers like Oumuamua years before. Her experience enabled her to recognize the subtle irregularities in 3I Atlas's motion that others might have dismissed as computational noise. Alongside her, Dr. Takashi Mori, an orbital dynamics specialist from the Subaru Observatory, ran simulations with an array of gravitational models, including perturbations from Mars, Jupiter, and even the Sun's relativistic effects. Their collaborative insight identified that the object's acceleration and trajectory were inconsistent with standard models, marking the first moment the scientific community confronted the impossible. Complementing ground-based efforts were automated surveys, such as the Pan-STARRS telescopes, designed to scan the sky for moving objects. When data from these systems flagged the unusual trajectory, rapid cross-verification with human analysts confirmed that the anomaly was genuine. The discovery process became a choreography of observation, computation, and debate. Teams exchanged datasets in near real time, evaluating spectra, brightness variations, and orbital deviations. Every measurement had to be verified, every assumption challenged, because the stakes were unprecedented. A misinterpretation could falsely suggest an extraordinary phenomenon where none existed, while a failure to recognize reality could squander a rare window into interstellar processes. The discoverers were conscious that 3I Atlas represented more than a mere object, it was a messenger from beyond the solar system. Their meticulous attention to detail and interdisciplinary coordination ensured that the first true understanding of the anomaly emerged from layers of observation and computation. Without their insight, the acceleration near Mars might have gone unnoticed, and the cosmic alarm, which would soon reverberate across the global scientific community, might have sounded too late. In that sense, the object's story began not just with the celestial mechanics of space, but with the vigilance and expertise of those willing to confront the extraordinary. Within hours of confirming the irregular behavior of 3I Atlas, NASA issued its first formal alert, a carefully worded notice to observatories, research institutions, and space agencies worldwide. It was not a declaration of imminent danger, but a recognition that this object defied existing predictions and required immediate, coordinated observation. The alert emphasized the object's approach near Mars, its unusual acceleration, and its spectral anomalies, instructing teams to prioritize its tracking across multiple wavelengths and instrumentation platforms. Control rooms at NASA's Jet Propulsion Laboratory and Goddard Space Flight Center shifted into heightened operational states. Satellites and telescopes were retasked, computer models were recalibrated, and observation schedules were rewritten. Every orbital asset capable of detecting the object from Hubble and Chandra to the Mars Reconnaissance Orbiter was considered for potential contribution. Engineers and scientists collaborated in shifts around the clock, knowing that even minutes could matter in gathering high-resolution data on this enigmatic visitor. The alert triggered an immediate response in the scientific community beyond the United States. ESA, JAXA, and various observatories in South America, Europe, and Asia began coordinating with NASA, sharing data streams and observational protocols. The object, invisible to casual skywatchers, had become the focal point of a global network of eyes trained on the heavens. For the first time in years, an interstellar object demanded full-scale international collaboration, reminiscent of the efforts to study Oumuamua, but with a more urgent tone. Its proximity to Mars introduced an added layer of curiosity and potential consequence. Even within NASA, the atmosphere was electric. The anomaly represented both a challenge and an opportunity to observe interstellar phenomena in real time, to test the limits of instrumentation, and to refine theoretical models of celestial mechanics. Press briefings were carefully managed, balancing public fascination with measured scientific caution. Internally, however, scientists debated the implications, running simulations of potential interactions with Mars, exploring hypothetical propulsion models, and questioning whether unseen forces, natural or otherwise, could explain the observed behavior. This alert marked the transition from discovery to active engagement. The cosmic alarm had moved from observation logs to coordinated scientific mobilization. 3I Atlas was no longer a distant curiosity. It was a near Mars phenomenon, challenging not only our understanding of interstellar objects but also the mechanisms of rapid, organized global scientific response. In this sense, the alert was both a warning and an invitation, a call to explore, measure, and perhaps to witness the impossible. Once the NASA alert circulated, observatories around the world shifted into overdrive. Streams of data began pouring in from an array of instruments: optical telescopes, infrared arrays, radar facilities, and space-based observatories. Every photon, every shift in reflected light was meticulously logged, catalogued, and compared. The sheer volume of information was staggering. Within hours, petabytes of raw measurements flooded servers, challenging data processing pipelines and testing the limits of storage and computational capacity. Scientists worked feverishly to distill meaningful patterns from this torrent, aware that each delay could obscure crucial insights into the behavior of 3I Atlas. The object's rapid acceleration and unorthodox trajectory required multiple triangulations. Ground-based arrays measured parallax, while space telescopes provided high-resolution imaging unaffected by atmospheric distortions. Simultaneously, radar measurements provided three-dimensional reconstructions of shape, spin, and reflectivity. Spectroscopic analysis across ultraviolet, visible, and infrared wavelengths delivered complex chemical signatures. Integrating these diverse data streams demanded not only raw computational power, but deep expertise in astrophysics, orbital mechanics, and materials science. Teams collaborated virtually across continents, often working around the clock to ensure that the anomaly was captured in every measurable detail. Despite the deluge, patterns began to emerge. Variations in brightness hinted at an irregular, perhaps metallic surface, while unexpected fluctuations in trajectory suggested forces acting in ways beyond simple gravitation. Each dataset, however, also contained contradictions, compelling teams to iterate on models and recalibrate instruments. The intensity of observation, combined with the object's proximity to Mars, provided an unprecedented opportunity, a natural laboratory in which interstellar material could be studied in situ under conditions never before observed. The data flood also amplified the philosophical weight of the moment. As night after night of observations filled servers and notebooks, scientists became increasingly aware that they were witnessing something fundamentally new, a body that challenged assumptions, tested predictive models, and refused categorization. The raw numbers, angles, reflectivities, velocities became more than measurements. They were clues in a profound cosmic riddle. The collaboration itself, a convergence of minds, machines, and global coordination, mirrored the vastness of space. Multiple perspectives converging to interpret a phenomenon that no single observer could fully grasp alone. In this cascade of information, the universe spoke in photons, radio waves, and infrared heat, leaving humanity to listen intently. 3I Atlas was no longer merely an interstellar visitor. It was a signal, an enigma, a challenge to the very frameworks through which we understand motion, matter, and the laws of the cosmos. The flood of data was both overwhelming and illuminating, a deluge through which the contours of an impossible trajectory slowly began to take shape. As the accumulated observations of 3I Atlas were analyzed, it became painfully clear that its trajectory refused to conform to any pre-existing model. Conventional orbital mechanics, rooted in centuries of Newtonian and Einsteinian calculations, could not account for the subtle yet unmistakable deviations recorded over days of observation. The object's path near Mars exhibited a slight but measurable acceleration coupled with lateral shifts that seemed almost deliberate, though no known natural forces could account for them. This unpredictability introduced a new layer of confusion and concern within the global scientific community. Astrophysicists and orbital dynamicists attempted to reconcile these anomalies through increasingly sophisticated simulations. Each model incorporated gravitational influences from Mars, its moons, Jupiter, and even relativistic corrections from the Sun's mass. Tidal forces, solar radiation pressure, and the Yarkovsky effect were considered, yet none could reproduce the observed trajectory. With every iteration, residuals persisted, small yet significant discrepancies between predicted and actual positions. These residuals, while minor in absolute distance, represented profound deviations in terms of energy and momentum for an object of its mass and composition. The confusion extended beyond mathematics. The object's apparent resistance to gravitational perturbations implied either a previously unknown property of interstellar bodies or an influence outside conventional physics. Observational teams debated whether 3I Atlas might harbor volatile outgassing undetectable with current instruments, or perhaps possess a magnetic or electrical field interacting with the solar environment. Yet no model, no matter how creative, fully explained the acceleration or the unexpected curvature of its path near Mars. This trajectory confusion had practical consequences. Projections of closest approach varied by tens of thousands of kilometers depending on which model was used, forcing Mars-orbiting satellites to adjust scanning schedules and forcing scientists to revise predictions of potential interactions. Even minor deviations in the object's course could dramatically affect risk assessments, not only for Mars, but for the broader inner solar system. Philosophically, the confusion underscored humanity's limited understanding of interstellar phenomena. The universe had presented an object that refused categorization, defied expectation, and operated under principles that were, at least temporarily, beyond comprehension. 3I Atlas's trajectory was a subtle, persistent reminder that even with our most precise instruments, the cosmos retained the power to surprise, challenge, and redefine the boundaries of knowledge. As the observational focus intensified, attention shifted from the motion of 3I Atlas to its physical surface. Radar and optical measurements began revealing details that only deepened the mystery. Unlike typical interstellar objects, which often exhibit irregular, rough textures resulting from eons of cosmic abrasion, 3I Atlas displayed regions of unexpected smoothness and high reflectivity. Certain facets gleamed in sunlight, suggesting the presence of metallic compounds or highly compacted minerals, yet the distribution of these reflective patches appeared almost deliberate, too uniform and coherent to be purely natural. Spectroscopic analysis further highlighted anomalies. While the presence of nickel and iron alloys was unusual but conceivable for an asteroid, the object also reflected elements in unusual ratios, including traces of exotic metals rarely found in the solar system. The combined spectral signatures suggested a formation environment radically different from known celestial bodies, possibly originating in a distant, metal-rich star system with unique stellar processes. No familiar asteroid class could account for the simultaneous combination of metallic luster, irregular shape, and inert behavior in solar radiation. High-resolution imaging revealed additional mysteries. Certain protrusions on the object's surface exhibited angular geometries that hinted at non-random formation processes, producing shadow patterns inconsistent with erosion or collision-based sculpting. As it rotated, subtle changes in brightness suggested that parts of its surface were denser or more reflective than expected, creating a visual rhythm that fascinated and perplexed astronomers alike. Even more striking was the object's lack of common cometary features. No tail, no coma, no visible gas emissions, even when exposed to increasing solar heat during its approach. The absence of outgassing implied a composition remarkably resistant to thermal stress and solar irradiation, a quality uncharacteristic of volatile-rich bodies. Combined with the metallic surface anomalies, this resistance lent an air of almost otherworldly durability to the object, as if it had traversed the interstellar void for eons without suffering measurable degradation. These surface anomalies not only complicated scientific understanding, but also prompted philosophical reflection. Here was an object that had survived unknown interstellar environments, whose physical properties defied conventional classification. It was simultaneously alien and coherent, reflecting a narrative of formation, endurance, and cosmic history that human instruments could only begin to decode. Each reflective glint, each unexpected ridge, told a story of a universe more intricate and enigmatic than previously imagined, inviting contemplation as much as measurement. To contextualize the extraordinary nature of 3I Atlas, scientists turned to the scant precedents of interstellar objects observed within the solar system. Chief among these was 1I Oumuamua, the first confirmed interstellar visitor detected in 2017. Its elongated shape, unusual brightness fluctuations, and lack of a detectable cometary tail had already challenged preconceptions about natural celestial bodies. Yet compared to 3I Atlas, Oumuamua's peculiarities were comparatively subtle, whereas Oumuamua's trajectory could eventually be reconciled through minor non-gravitational accelerations. 3I Atlas exhibited active deviations near Mars, a magnitude and complexity far beyond what had been previously recorded. Scientists also reviewed 2I Borisov, a later interstellar comet observed in 2019, which conformed more closely to known cometary behavior with outgassing and predictable orbital mechanics. While Borisov provided a useful benchmark for chemical composition and velocity, it lacked the surface anomalies, metallic reflections, and unpredictable maneuvering that defined 3I Atlas. By juxtaposing these prior cases, researchers could appreciate how dramatically the new visitor stretched the boundaries of interstellar observation. Archival data and simulations were revisited to identify potential overlooked precedents. Were there objects previously catalogued as anomalies that, in hindsight, might have been similar? Most historical records lacked sufficient resolution or multi-wavelength analysis to draw definitive parallels. Nevertheless, the comparative approach underscored that 3I Atlas was not merely unusual, it was unprecedented, entering uncharted territory both physically and behaviorally. These historical comparisons illuminated a continuum of interstellar phenomena, revealing patterns and deviations, yet also emphasized the uniqueness of the current event. 3I Atlas did not simply extend prior observations, it demanded a rethinking of what was considered possible for bodies originating beyond the solar system. Its trajectory, composition, and near-Mars behavior collectively formed a case study unlike any other, one that would influence the framing of interstellar research for years to come. The broader implication was clear. Humanity was witnessing a step in cosmic evolution that had rarely, if ever, been recorded, a natural object behaving in ways that defied prior understanding. Historical comparisons provided both perspective and a measure of awe, reminding scientists and the public alike that the universe contains phenomena still fully beyond our grasp, inviting humility and curiosity in equal measure. Detailed spectroscopic analyses of 3I Atlas revealed anomalies that further separated it from known interstellar objects. Light reflected off its surface contained signatures of metals in unusual proportions, including nickel, iron, and even rarer elements such as iridium and platinum group metals, which are typically dispersed in trace quantities within known asteroids. Yet, these elements appeared concentrated in regions that suggested a history of either extreme natural refinement or processes entirely unfamiliar to terrestrial science. The patterns of absorption and emission lines hinted at an intricate, heterogeneous surface, one that absorbed certain wavelengths while reflecting others in a manner inconsistent with simple metallic or rocky compositions. Infrared spectroscopy revealed unexpected thermal properties. Unlike standard asteroids or comets, which heat and radiate predictably under solar influence, portions of 3I Atlas's surface seemed almost thermally inert, resisting heat absorption, while nearby regions displayed anomalous radiative behavior. These thermal disparities suggested material properties that could survive intense interstellar travel without significant alteration, a resilience that surpassed even the most durable meteorites catalogued in our solar system. Scientists speculated that these patterns might indicate a composite structure, layering metals and refractory compounds in ways never observed before. Further anomalies arose in the near-ultraviolet spectrum, where faint emissions suggested the possible presence of complex organic compounds. These were not typical cometary volatiles, but rather stable organics, perhaps synthesized under conditions vastly different from those found in the solar system. Their presence raised questions about the object's formation environment, hinting at processes in distant star systems, or even unique chemical pathways yet to be studied. Spectral oddities compounded the mystery of 3I Atlas's behavior. Each measurement revealed more inconsistencies, elemental ratios that contradicted standard cosmochemistry, reflectivity patterns suggesting polished or engineered surfaces, and thermal responses that defied simple physics. The object, in essence, became a spectral puzzle, one whose chemical whispers challenged both observational techniques and theoretical frameworks. In reflecting on these findings, scientists recognized that 3I Atlas was not merely a visitor from another star system. It was an emissary of phenomena that our instruments had not been designed to interpret fully. Each spectral oddity was a testament to the universe's ability to surprise, to present structures and compositions far beyond human expectation. The object's light, traveling billions of kilometers across the void, carried encoded stories of cosmic environments, stellar processes, and perhaps physical laws that remained partially obscured, waiting for human ingenuity to decode. As 3I Atlas drew nearer to Mars, the subtle interplay of gravitational forces became increasingly pronounced, revealing anomalies that confounded scientists. Mars-orbiting satellites detected minuscule perturbations, slight shifts in orbiting trajectories, and unanticipated variations in local gravitational fields. While these deviations were small in absolute magnitude, they were significant enough to suggest that the interstellar visitor was exerting forces inconsistent with its estimated mass. Traditional calculations could not account for the localized gravitational influence, leaving researchers to speculate about hidden mechanisms or unconventional physical properties. The effect was not limited to orbiters alone. Simulations of Mars's gravitational field, integrating real-time data from multiple satellites, indicated minor but detectable distortions, coinciding with 3I Atlas's passage. These distortions did not match expectations based on a purely Newtonian gravitational model, nor could they be explained by tidal forces alone. The cumulative data suggested that either the object possessed an anomalously dense or magnetically interactive mass distribution, or that unknown forces were subtly influencing the surrounding space. Ground-based observatories contributed complementary measurements, tracking changes in Mars's apparent position relative to background stars. By combining optical tracking with radar observations, scientists inferred that the local spacetime curvature around the planet was temporarily affected in ways not predicted by classical mechanics. The perturbations were extremely small fractions of a millimeter per second, but consistent across multiple independent observations, reinforcing the reality of the anomaly. These gravitational effects prompted deeper theoretical exploration. Some researchers proposed that 3I Atlas could be interacting with dark matter in ways that locally amplified its effective gravitational influence. Others suggested more exotic explanations, including transient spacetime distortions or local deviations in the inertial frame of reference. While these hypotheses remained speculative, the gravitational anomalies underscored a profound truth. 3I Atlas was not only behaving in ways physically unusual for an interstellar object, it was actively challenging the assumptions underlying centuries of celestial mechanics. The discovery added a tangible, measurable layer to the cosmic mystery. Unlike trajectory deviations observed from a distance, these gravitational effects impacted actual spacecraft and planetary motion, creating a direct link between the enigmatic visitor and human technology. The universe, it seemed, had provided both a puzzle and a test, revealing through subtle gravitational whispers that even small deviations could hold vast implications for our understanding of interstellar physics and the intricate dance of planetary bodies. Amid the mounting anomalies, the notion of propulsion, whether natural or artificial, entered the scientific discourse. The subtle acceleration of 3I Atlas near Mars, its unexpected lateral movements, and its resistance to gravitational prediction collectively suggested forces at work beyond passive celestial mechanics. For decades, interstellar objects had been assumed to drift silently, shaped solely by gravity and radiation pressure. Yet, this object seemed almost purposeful, prompting cautious speculation about possible propulsion mechanism. Natural propulsion hypotheses considered several phenomena. Outgassing, for example, is known to alter cometary trajectories, but 3I Atlas displayed negligible evidence of volatile release. Even undetectable micro-outgassing would have to be both precisely directed and extraordinarily energetic to explain the observed accelerations, straining credibility. Alternative natural mechanisms included solar radiation pressure acting on highly reflective surfaces or interactions with sparse interplanetary plasma. While mathematically feasible, these explanations required extreme conditions, exceptionally high surface reflectivity, precise orientation relative to the Sun, and extraordinary material coherence across the object's mass. Artificial propulsion, though speculative, could not be entirely dismissed. The uniformity of acceleration, combined with the irregular surface and reflective anomalies, led some theorists to consider the possibility of engineered forces. Such forces might include directed energy propulsion, magnetically induced momentum, or even interactions with exotic energy fields unknown to contemporary physics. While these ideas bordered on science fiction, they remained within the realm of rigorous thought experiments. particularly when all natural mechanisms appeared insufficient. Computational models tested both natural and artificial scenarios. Simulations incorporating hypothetical propulsion systems could reproduce segments of 3I atlas's observed behavior, yet no single model accounted fully for every deviation in trajectory, spin, and acceleration. This partial success reinforced the mystery rather than resolving it, highlighting the limits of current understanding. Scientists remained cautious, framing propulsion as a possible explanatory category rather than a definitive claim. The consideration of propulsion, whether natural or artificial, added dramatic weight to the ongoing investigation. It challenged assumptions about interstellar wanderers, raised philosophical questions about agency and cosmic intelligence, and demanded a re-evaluation of the forces governing small bodies in space. 3I Atlas had become more than a passive traveler. It was an active puzzle, compelling humanity to explore the boundaries between natural, celestial dynamics and phenomena that might hint at unknown mechanisms or technologies in the cosmos. The scientific community soon realized that 3 Atlas's behavior was sending metaphorical shockwaves through the frameworks of astrophysics and planetary science. Each new observation, unexpected acceleration, lateral deviations, metallic surface, anomalies, and spectral irregularities forced theorists to re-examine fundamental principles long considered settled. Newtonian mechanics, while immensely successful for centuries, now appeared insufficient to account for the object's complex dynamics. Even Einstein's relativistic corrections, typically invoked for objects moving at substantial fractions of light speed, could explain only a fraction of the anomalies. These shockwaves manifested not only in computational models, but in the philosophical foundations of physics. If a natural interstellar object could exhibit such behavior, then assumptions about inertial stability, energy distribution, and cosmic evolution required reconsideration. Could there be forces in the galaxy interacting selectively with certain interstellar masses? Were there previously undetected interactions between exotic matter and standard baryonic matter that only revealed themselves under rare circumstances? Each hypothesis sent tremors through academic discourse, prompting a rethinking of long-held notions about how matter moves through interstellar space. In laboratories, theorists proposed thought experiments to reconcile the data. Could quantum field fluctuations produce measurable macroscopic effects on a body the size of 3I Atlas? Might hidden dimensions, as suggested in some string theory models, exert subtle influences on the trajectories of interstellar visitors? Even highly speculative ideas, such as local spacetime warping or controlled interactions with dark energy, were entertained not as definitive explanations, but as frameworks to stimulate calculation, observation, and debate. The shock waves extended beyond theory into instrumentation and methodology. Observatories were forced to recalibrate sensors, design new observation protocols, and develop software capable of modeling behaviors previously considered impossible. Data pipelines were stress-tested against edge case anomalies, ensuring that no subtle deviation went unnoticed. Across universities and space agencies, seminars and conferences erupted around the object's characteristics, each session exploring its implications for physics, astronomy, and cosmology. Through it all, the emotional undercurrent of awe was palpable. 3I Atlas was more than an interstellar body. It was a provocation from the universe, an enigma that questioned our ability to predict, categorize, and understand. The shockwaves in theory were not mere intellectual tremors. They were a profound reminder that the cosmos remains an active teacher, capable of challenging the most confident minds with phenomena that defy expectation, inviting humility, curiosity, and relentless inquiry. As data from 3I Atlas accumulated, the the scientific community entered a phase of intense debate, with divergent interpretations reflecting both the object's complexity and the limits of current understanding. In conferences, online forums, and working groups spanning continents, astrophysicists, planetary scientists, and theoretical physicists engaged in rigorous discussions, each interpreting the measurements through distinct lenses. Some argued for exotic natural processes, while others proposed the possibility of unknown artificial or highly engineered mechanisms, carefully avoiding sensationalism but acknowledging the difficulty of conventional explanations. The debates often centered on the plausibility of propulsion versus natural causes. Proponents of natural explanations emphasized that interstellar bodies might experience subtle accelerations from solar radiation pressure or asymmetrical mass distributions, phenomena that, though rare, could produce effects misinterpreted as impossible. Critics countered that the magnitude and directionality of 3I Atlas's deviations exceeded expected ranges, challenging even advanced computational models. Spectral oddities, combined with unusual surface properties and rotational behavior, further fueled disagreement, prompting calls for expanded observation campaigns and new simulation frameworks. Beyond mechanics, some theoretical physicists suggested that the object might provide indirect evidence of interactions with dark matter or other exotic fields. These proposals, while highly speculative, were grounded in emerging physics literature and supported by partial correlations between observed anomalies and predictions from advanced models. Papers circulated rapidly, some peer-reviewed, others preprints, each offering alternative interpretations, each sparking vigorous commentary. The debates, though sometimes heated, were a testament to the scientific method in action. Hypotheses proposed, tested against data, refined, and challenged through collaborative scrutiny. Public interest, while secondary to rigorous analysis, added another dimension. Media outlets reporting cautiously on the unusual observations led to philosophical discussions among scientists about communication and the portrayal of uncertainty. Researchers balanced the need to share fascinating developments with the imperative to avoid overstating conclusions, mindful that premature speculation could distort public understanding. Amidst the intensity, a unifying theme emerged. No single model fully explained. 3. Atlas. The debates, far from undermining confidence, underscored the object's significance. It was a catalyst for collaborative problem-solving, a stimulus for refining theoretical frameworks, and a vivid reminder that the cosmos can challenge not only our observations but the interpretive frameworks we bring to them. The peer debate intensified, but in that intensity lay a collective journey toward understanding a phenomenon that was as enigmatic as it was enlightening. With the global consensus on 3I Atlas's anomalous nature solidifying, a coordinated campaign of deep, multi-wavelength observation commenced. Space-based telescopes, including Hubble, Chandra, and the James Webb Space Telescope, trained their precise instruments on the interstellar visitor, capturing light from ultraviolet to infrared with unprecedented resolution. Simultaneously, ground-based facilities across the globe reoriented optical, radar, and spectroscopic arrays to ensure near-continuous monitoring. The goal was clear: extract every measurable detail about the object before it moved beyond observational reach, and decipher the physics governing its impossible behavior. The data acquisition strategy was meticulous. Photometric imaging tracked subtle variations in brightness, revealing rotational dynamics and albedo contrasts across the surface. Spectroscopy probed chemical composition, aiming to identify both metallic and organic constituents. Infrared observations measured thermal inertia, highlighting areas of unusual heat absorption or retention. Radar mapping reconstructed three-dimensional shapes, confirming irregular, elongated structures with facets and ridges that challenged conventional formation theories. Every new dataset reinforced the object's extraordinary nature, revealing patterns that hinted at coherence, resilience, and perhaps a design beyond purely natural processes. Observational campaigns also employed synchronized triangulation, telescopes on separate continents and in orbit simultaneously captured angles and parallax, allowing scientists to refine models of trajectory and acceleration with unmatched precision. Small perturbations in Mars's gravity, combined with Doppler shifts in reflected light, were integrated into comprehensive simulations. Teams monitored each rotation of the object, noting subtle changes that might indicate internal mass redistribution, surface heterogeneity, or interactions with local space environments. These deep observations revealed phenomena previously unrecorded in interstellar objects. Metallic reflections fluctuated with rotation in a non-uniform manner, suggesting a heterogeneous composition or surface treatment. Thermal anomalies persisted across multiple rotations, resisting explanations based on simple solar heating models. Even as sophisticated simulations attempted to replicate these behaviors, discrepancies persisted, emphasizing the limits of current theoretical frameworks. The deep observation phase elevated 3I Atlas from a mere curiosity to a case study in interstellar physics. The richness of data offered both challenge and opportunity, a chance to test models, expand understanding of interstellar bodies, and confront the boundaries of what is physically possible. As telescopes and satellites hummed across wavelengths, humanity's gaze was locked upon this visitor, a silent interlocutor from the depths of space, revealing itself through the delicate language of light, radiation, and motion. As 3I Atlas continued its approach, precise photometric analysis revealed a rotation rate that confounded expectations. Measurements showed the object spinning at a rate unusually rapid for its size and composition, with a complex precession of its axis that suggested more than simple tumbling. While most small interstellar bodies rotate predictably or exhibit gradual changes in spin due to collisions and outgassing, 3I Atlas's rotation was both stable and irregular, hinting at structural properties or forces far beyond the ordinary. High-resolution imaging captured subtle changes in reflected light with each rotation, revealing alternating bright and dark facets. These shifts were not merely reflective of surface albedo, but suggested topographical and compositional heterogeneity. Observers noted that certain metallic regions aligned with rotational phases in ways that could amplify radiation pressure effects, perhaps contributing to observed trajectory anomalies. The interplay of rotation and surface composition appeared almost choreographed, as if governed by principles distinct from standard mechanical expectations. The rapid spin also raised questions about structural integrity. Conventional calculations predicted that a body of 3I Atlas's estimated size, composed largely of metallic and rocky material, would fragment under such rotational stress. Yet it remained intact, implying either extraordinarily cohesive internal bonding or a previously unobserved material property. Some theorists posited that the internal structure might include layered alloys or composites unusually resistant to centrifugal forces. Others considered more speculative notions, including self-stabilizing fields or interactions with external forces that counteracted rotational stress. Rotation observations also added nuance to gravitational models. The precessing spin influenced how 3I Atlas interacted with Mars's local gravitational field, complicating predictions of minute orbital perturbations. The object's angular momentum introduced additional variables that required continuous recalibration of both predictive models and observational strategies. In effect, the rotation became a dynamic parameter, inseparable from trajectory, surface anomalies, and thermal behavior. Philosophically, the unexpected rotation contributed to a growing sense of wonder. Here was a visitor from the interstellar void, behaving in ways that defied conventional mechanical laws yet remained internally consistent. Its spinning, reflecting light across the Martian sky, was a visible manifestation of the universe's capacity for complexity and surprise. The phenomenon invited reflection on the subtle interplay between matter, energy, and motion, and on the realization that even objects appearing inert can embody layers of physical sophistication beyond human anticipation. Amid the growing catalogue of anomalies, 3I Atlas revealed yet another layer of complexity: unexpected magnetic properties. Sensitive magnetometers aboard Mars-orbiting satellites, calibrated to detect the faintest perturbations in the planetary magnetic field, registered minute but persistent fluctuations coinciding with the object's passage. These signals were subtle yet consistent across multiple instruments, indicating that 3I Atlas possessed localized magnetic fields, unlike those typically observed in interstellar debris. The magnetic anomalies posed immediate questions about composition and internal structure. While certain metals can generate or influence magnetic fields, the strength and orientation detected suggested an organized, heterogeneous distribution within the object. Unlike natural ferromagnetic alignment expected in metallic asteroids, these fields appeared non-uniform and dynamically interacting with the surrounding solar wind. The fluctuations indicated that the object might influence charged particles in its vicinity, potentially contributing to its peculiar trajectory or resistance to predicted orbital forces. Simulations explored potential interactions with Mars's magnetosphere and solar radiation. Models suggested that the object's magnetic properties could create subtle perturbations in satellite trajectories or ionized particle flows. Although these effects were minimal in scale, they reinforced the notion that 3I Atlas was not passive but actively engaged through physical properties with the environment around it. Some theorists proposed that the magnetic signatures might arise from previously unknown crystallographic arrangements or exotic alloys formed in interstellar conditions, lending the object structural resilience and surface conductivity. The magnetic mysteries also prompted reflection on broader astrophysical implications. Interstellar objects with strong or organized magnetic fields could carry clues about the magnetic histories of their parent systems, revealing star formation, planetary differentiation, or even technological manipulation in speculative scenarios. 3I Atlas, in this sense, was not just a visitor to Mars, but a messenger of unseen cosmic forces, a physical record of processes occurring in environments beyond the reach of direct observation. In labs and observatories, researchers debated the origin of the magnetic phenomena. Were they intrinsic to the object, or were they the result of interactions with solar wind and planetary magnetospheres? Regardless, the effect was undeniable, adding yet another dimension to the puzzle. 3I Atlas, through its magnetic presence, had expanded the perimeter of known interstellar complexity, challenging assumptions, stimulating theory, and compelling humanity to consider magnetic forces as integral to the enigmatic behavior of objects traveling across the cosmic void. To understand 3I Atlas fully, scientists began placing it within the broader framework of galactic dynamics. Unlike objects confined to the solar system, this interstellar visitor had traversed light years of space, likely originating from a distant star system far beyond the nearest stellar neighbors. Its journey spanned interstellar voids, regions of sparse gas, cosmic dust, and radiation fields capable of eroding or altering less resilient bodies. That it had maintained structural integrity, magnetic coherence, and surface stability suggested a composition honed to survive extreme conditions and hinted at formation processes radically different from those familiar in our solar system. The galactic trajectory of 3I Atlas raised questions about the environment from which it emerged. Could it have been ejected during the gravitational interactions of a dense stellar cluster? Was it a fragment of a larger planetary body, expelled during a cataclysmic event such as a supernova or stellar collision? Understanding its origin required modeling not just solar system physics, but galactic gravitational dynamics, stellar evolution, and the chaotic ballet of interstellar matter over millions of years. Comparisons with previous interstellar objects illuminated patterns, yet underscored uniqueness. Unlike 1I Oumuamua, whose elongated shape suggested tidal stresses during ejection, or 2I Borisov, whose cometary outgassing mirrored solar system analogues, 3I Atlas appeared engineered by natural forces that were both extreme and highly selective. Its reflective metallic patches, magnetic anomalies, and unexpected acceleration suggested that either the galactic environment had imparted these features over aeons, or that processes within its originating system were uniquely capable of producing such resilience and complexity. Placing 3I Atlas in cosmic context also highlighted its statistical rarity. Interstellar objects entering the inner solar system are exceedingly uncommon, detected perhaps once per decade at current observational sensitivity. To observe one performing such extraordinary behaviors near Mars emphasized the importance of both chance and technological preparedness. It was a reminder that the universe, vast and sparsely populated, occasionally offers glimpses into processes and bodies that test the limits of human comprehension. This contextual perspective framed the visitor not simply as a local anomaly, but as a node in a vast cosmic network of material and energy flows. Understanding it demanded a multi-scale approach, from atomic composition to galactic trajectory, integrating astrophysics, planetary science, and speculative modeling. In doing so, 3I Atlas became more than a transient object. It was a symbol of interstellar connection, a bridge between the known and the unfathomable, and a profound reminder of the universe's enduring complexity. With mounting evidence and a growing collection of anomalies, scientists began formulating leading hypotheses to explain 3I Atlas. The first category centered on exotic natural mechanisms. Some researchers suggested that interactions with dark matter could produce subtle forces influencing its acceleration and trajectory. In this scenario, the object, as it passed through regions of higher dark matter density near Mars, might have experienced forces not accounted for by classical gravitation. While speculative, these models were grounded in extensions of particle physics and cosmological theory, offering a potential natural explanation for the apparent impossible maneuvers. Other natural hypotheses explored the role of internal heterogeneity. Layers of metallic and refractory compounds within 3I Atlas could have responded differentially to solar radiation, creating asymmetrical forces capable of producing minor accelerations. Coupled with rapid rotation and reflective surfaces, these factors might generate cumulative deviations that, over millions of kilometers, resulted in observable trajectory anomalies. Computational models incorporating these effects could reproduce segments of its behavior, though not entirely accounting for the lateral deviations or precessional rotation observed. Artificial or engineered mechanisms, while controversial, were also considered with careful scientific rigor. Some theorists proposed that the object might be a relic of an extraterrestrial technological system, propelled or guided through space by controlled energy fields. These suggestions were not assertions of intelligent origin, but rather a framework for exploring non-natural explanations when all conventional physics failed. Models of directed propulsion, magnetic field interactions, or even controlled mass redistribution were tested in simulations, demonstrating partial consistency with observed behavior. Other hypotheses blended natural and speculative elements, including interactions with quantum fields, transient space-time distortions, or higher dimensional effects. While deeply theoretical, these models provided a scaffold for testing ideas beyond classical mechanics, pushing the boundaries of what observational data could imply about physics in extreme interstellar contexts. In all cases, leading hypotheses emphasize the extraordinary nature of 3I Atlas. No single explanation was wholly sufficient. Each accounted for fragments of observed behavior while leaving others unresolved. This multiplicity reflected the object's complexity and the novelty of its interstellar journey. 3I Atlas, through these hypotheses, challenged scientists to think creatively, rigorously, and expansively, reminding the community that the universe could behave in ways that were subtle, profound, and entirely unexpected. In attempting to explain 3I Atlas's anomalies, scientists turned to Einstein's theories of relativity, seeking insight into whether space-time curvature, relativistic effects, or gravitational time dilation could account for its unexpected motion. Although the object's velocity was far below the speed of light, subtle relativistic corrections were essential when modeling its trajectory near Mars, especially considering the precise accelerations and rotations observed. These effects, though minute, allowed theorists to examine the object's behavior with a degree of accuracy unattainable through classical mechanics alone. Relativistic modeling focused on how the curvature of spacetime around Mars and the Sun might interact with a highly compact, dense object. Even small deviations predicted by general relativity could accumulate over interstellar distances, potentially contributing to trajectory discrepancies. Calculations included perturbations caused by Mars's mass distribution and the influence of solar gravitational gradients. In addition, rotational precession and frame-dragging effects, though minimal, were incorporated to account for angular momentum interactions with the surrounding gravitational field. Scientists also explored whether relativistic phenomena could explain surface anomalies. Differential gravitational interactions along the object's elongated structure might produce microstresses influencing rotational behavior, potentially explaining its unexpected spin stability and precession. Similarly, variations in the local curvature of space-time could interact with surface metals in ways that subtly affected momentum, producing effects otherwise attributed to mysterious forces. These considerations did not offer a complete solution. Relativity explained portions of the observed behavior, but failed to account fully for lateral accelerations or magnetic anomalies. Nevertheless, incorporating Einsteinian frameworks provided a more comprehensive model, highlighting the importance of nuanced, multi-dimensional approaches when confronting an object that defies conventional understanding. Ultimately, relativity offered both clarity and humility. It reinforced that even well-established laws could illuminate only part of the picture, and that 3I Atlas's behavior existed at the intersection of classical physics, relativistic effects, and potentially unknown forces. By examining the object through the lens of spacetime itself, scientists gained a deeper appreciation for its complexity and for the subtle interplay of mass, motion, and the very fabric of the cosmos. As conventional and relativistic frameworks struggled to fully explain 3I Atlas, some theorists ventured into the domain of quantum mechanics and speculative physics. While quantum effects are typically confined to microscopic scales, extreme interstellar conditions prompted consideration of whether rare, large-scale quantum phenomena could manifest in ways measurable for a macroscopic body. Concepts such as quantum tunneling, vacuum fluctuations, or interactions with zero-point energy fields became part of serious modeling discussions, not as fringe ideas, but as potential mechanisms for the object's anomalous motion and resilience. One hypothesis proposed that 3I Atlas might interact with the quantum vacuum in a manner producing minute but persistent forces, subtly influencing its trajectory. Though these effects would be incredibly small under normal conditions, over interstellar distances and timescales, even infinitesimal deviations could accumulate into measurable acceleration near Mars. Models of this type required integration of quantum field theory with classical orbital mechanics, a challenging exercise at the intersection of multiple physics domains. Additionally, some researchers considered the possibility of localized quantum coherence within the object itself. Certain arrangements of exotic materials, particularly rare metallic alloys, might allow quasi-stable quantum states that influence mass distribution or surface interactions with ambient fields. While highly speculative, such models could account for observed rotational stability, resistance to centrifugal stress, and anomalous magnetic signatures, offering a unified framework to connect several of 3I Atlas's mysteries. Quantum considerations also introduced philosophical implications. If macroscopic quantum phenomena influenced interstellar objects, our understanding of classical determinism in celestial mechanics would require re-evaluation. Observing such effects would suggest that subtle, otherwise hidden layers of physics shape cosmic behavior, adding depth and complexity to the narrative of interstellar travel. Ultimately, quantum possibilities remained conjectural, yet they expanded the conceptual horizon of 3 Atlas studies. They emphasized that the universe might operate with layers of subtlety beyond human observation, and that even a single interstellar object could challenge assumptions, inspire new theoretical exploration, and prompt a re-evaluation of the limits of observable physics. With each day of observation, the global network of telescopes, satellites, and radar arrays intensified their scrutiny of 3I Atlas. Coordinated campaigns ensured continuous monitoring, capturing data across the electromagnetic spectrum from ultraviolet to radio frequencies and employing the full array of orbital and ground-based instruments. These efforts allowed scientists to refine trajectory predictions, track rotational dynamics, and observe surface and spectral anomalies in near real time, creating a comprehensive record of the object's behavior during its close approach to Mars. Mars-orbiting satellites, including the Mars Reconnaissance Orbiter and MAVEN, contributed high-resolution imagery and magnetic field readings, enabling precise measurements of gravitational and electromagnetic interactions. Ground-based optical telescopes provided complementary photometric and spectroscopic data, while radar arrays mapped structural features and rotation with remarkable detail. Every data point was integrated into simulations, offering insights into the interplay of physical forces and the object's dynamic properties. The monitoring effort was not merely observational but also predictive. Scientists constructed real-time models incorporating gravitational, magnetic, rotational, and thermal factors, updating forecasts of position, spin, and surface behavior continuously. Small discrepancies between predicted and observed positions prompted iterative refinements, enhancing both the understanding of 3I Atlas and the predictive capabilities of interstellar object modeling. In addition to professional observatories, Advanced amateur astronomers equipped with sensitive instrumentation contributed valuable observations. Their contributions augmented global datasets, filling temporal gaps and providing additional perspectives on the object's behavior. This collaborative network exemplified the integration of technology, expertise, and global coordination required to study an interstellar anomaly in unprecedented detail. Ongoing monitoring also revealed temporal changes in the object's properties. Slight variations in reflectivity, minor shifts in magnetic intensity, and subtle modifications in rotational phase suggested dynamic processes at work, perhaps driven by internal structural adjustments or interactions with the solar environment. Each observation offered new clues, gradually building a more complete, though still enigmatic, portrait of 3I Atlas. Through persistent vigilance, humanity gained an unparalleled window into interstellar phenomena. The object's passage became both a test of observational technology and a living laboratory, demonstrating how coordinated monitoring could capture the nuances of an impossible visitor. In doing so, it reinforced the broader scientific lesson: careful, continuous observation is essential for understanding even the most baffling cosmic enigmas. As 3I Atlas continued its near-Mars passage, scientists began evaluating potential risks associated with its unexpected behavior. While the object posed no immediate threat to Earth, its proximity to Mars warranted careful consideration. Calculations assessed gravitational perturbations, potential collision scenarios with Martian orbiters, and the long-term implications of any debris that might be shed due to rotational stress or surface instability. Even minor inaccuracies in trajectory prediction could have cascading effects, especially for satellites operating in low Mars orbit. Risk assessment required integrating multiple data streams: rotational dynamics, surface anomalies, and magnetic interactions were modeled alongside gravitational influences. Simulations considered extreme but plausible scenarios: fragments breaking off due to stress, magnetic interactions affecting satellite instrumentation, or minute gravitational tug altering orbital parameters. While none of these outcomes appeared imminent, the exercise underscored the necessity of proactive monitoring and scenario planning. The broader cosmic risk was also evaluated in theoretical terms. Could 3I Atlas or similar interstellar objects present threats to planetary systems if their trajectories are influenced unpredictably? While the probability was exceedingly low, the object's anomalous acceleration demonstrated that even a small interstellar body could behave in ways that challenge predictive models. These considerations were critical for mission planning, both for Mars orbiters and future interplanetary exploration. Scientists communicated risks carefully to avoid unnecessary alarm. The emphasis was on preparedness, data-driven predictions, and precautionary maneuvers rather than sensationalism. Meanwhile, the object's very existence prompted philosophical reflections. It reminded humanity of the intrinsic unpredictability of the cosmos, the potential hazards embedded in celestial mechanics, and the importance of maintaining vigilance in an environment defined by both beauty and danger. Ultimately, 3I Atlas's near-Mars passage reinforced the necessity of humility in the face of interstellar phenomena. While no catastrophic risk materialized, the meticulous modeling and monitoring highlighted how a single anomalous object could challenge assumptions, influence mission planning, and provide a vivid illustration of the universe's unpredictable intricacies. Humanity, attentive yet patient, observed and learned, fully aware that understanding and caution were inseparable companions when confronting the unknown. Amid the torrent of observational data, scientists began to detect subtle patterns in 3I Atlas's behavior. Its trajectory, though irregular at first glance, exhibited recurring deviations at predictable rotational phases, suggesting an underlying order amid apparent chaos. Each spin revealed consistent alignments between reflective metallic regions and lateral acceleration vectors, hinting that structural or compositional asymmetries influenced motion. These emergent patterns provided the first coherent hints that the object's anomalies were not random, but instead followed physical principles that were previously unconsidered in celestial mechanics. Spectroscopic observations added further layers to the emerging patterns. Specific elemental concentrations corresponded with reflective anomalies, indicating that metallic-rich regions might be influencing the object's interaction with solar radiation or the interplanetary magnetic field. Thermal imaging showed that these same regions absorbed and re-radiated energy differently than adjacent surfaces, subtly affecting rotational dynamics. The combination of chemical, structural, and rotational patterns painted a picture of an object exhibiting complex, interdependent behaviors across multiple physical domains. Even magnetic measurements suggested recurring patterns. Fluctuations in local magnetic fields correlated with rotational phase and surface composition, indicating that magnetic interactions could be contributing to the object's trajectory and acceleration. This interplay between rotation, composition, and magnetism hinted at a coherent system of forces acting upon 3I Atlas, reinforcing the idea that the anomalies were intrinsic rather than artifacts of measurement or environmental perturbations. The emergence of these patterns allowed scientists to refine models, narrowing uncertainties in trajectory predictions and improving understanding of rotational behavior. While the full explanation remained elusive, recognizing order within complexity provided a framework for future investigation. Patterns suggested that even phenomena initially perceived as impossible could adhere to underlying physical principles once fully understood. In the broader cosmic perspective, these emergent patterns highlighted the intricate choreography of matter and energy at interstellar scales. 3I Atlas, once a chaotic enigma, revealed a degree of coherence that invited both awe and contemplation, illustrating that the universe, even in its most mysterious manifestations, often conceals a hidden structure, waiting for observation and analysis to uncover its logic. The unfolding mystery of 3I Atlas prompted an unprecedented level of collaboration among the global scientific community. Observatories, universities, and space agencies coordinated data collection, analysis, and theoretical modeling, creating a network of expertise that spanned continents and disciplines. Optical, infrared, ultraviolet, and radar datasets were shared in near real time, enabling teams to cross-validate findings and integrate observations into coherent models. This collaborative infrastructure allowed the scientific community to monitor the object continuously, refine predictions, and explore hypotheses with a breadth impossible for any single institution. Coordination extended beyond professional astronomers. Advanced amateur astronomers, equipped with high-quality instruments, contributed critical observations during periods when major telescopes were unavailable. Their meticulous tracking and photometric measurements supplemented global datasets, ensuring temporal continuity and enhancing the resolution of rotational and trajectory analyses. Open communication channels allowed data to flow rapidly, enabling near-instant feedback between teams and iterative refinement of models. Interdisciplinary collaboration was equally essential. Astrophysicists, planetary scientists, chemists, and theoretical physicists worked together to interpret the diverse anomalies of 3I Atlas. Chemists analyzed spectral data to infer surface composition, while physicists modeled rotational dynamics and potential forces. Magnetic and thermal measurements were integrated into comprehensive simulations, bridging observational data with theoretical frameworks. This holistic approach facilitated the emergence of patterns in trajectory, spin, and composition, providing insights inaccessible to siloed analyses. Scientific collaboration also spurred rapid publication and debate. Preprints, shared datasets, and conference presentations circulated worldwide, allowing ideas to be tested, challenged, and refined in real time. This open exchange accelerated understanding, ensuring that no single perspective dominated interpretation and that multiple models could be assessed simultaneously. Ultimately, the global collaboration transformed the study of 3I Atlas into a collective endeavor, exemplifying the strength of coordinated human inquiry. The object, mysterious and anomalous, became a catalyst for unity, intellectual rigor, and shared exploration. Through this cooperation, humanity gained not only data about a unique interstellar visitor, but also a demonstration of how collective effort can confront the profound enigmas of the cosmos, advancing knowledge far beyond what individual efforts could achieve alone. Beyond the empirical data and theoretical debates, 3I Atlas inspired profound philosophical reflection. Its presence near Mars, behaving in ways that defied expectation, prompted scientists and thinkers alike to reconsider humanity's place within the cosmos. The universe, vast and largely indifferent, had presented an object that challenged not only technical understanding, but also conceptual frameworks of order, causality, and predictability. In observing this interstellar traveler, humanity confronted questions about the limits of knowledge, the nature of anomaly, and the potential existence of forces or phenomena yet undiscovered. The philosophical weight of 3I Atlas lay in its capacity to evoke both humility and wonder. Centuries of astronomical observation had conditioned humanity to anticipate patterns and regularities, elliptical orbits, predictable trajectories, repeatable behavior. Yet this object demonstrated that the cosmos could surprise, that interstellar environments might produce bodies with properties beyond terrestrial imagination. It raised fundamental questions. Are these anomalies rare exceptions, or do they hint at a richer, more complex universe? How should science reconcile the tension between observed regularity and unexpected singularities? Moreover, 3I Atlas provoked reflection on the nature of observation itself. The process of studying the object required coordinated human ingenuity, technological sophistication, and interpretive creativity. Each measurement was a collaboration across space, time, and disciplines, emphasizing that understanding the universe is as much an intellectual and philosophical endeavor as a technical one. The object became a mirror, reflecting the strengths and limitations of human cognition, the provisional nature of scientific truth, and the beauty inherent in the pursuit of understanding. Finally, the encounter invited contemplation of cosmic significance. 3I Atlas, traversing light years before approaching Mars, reminded humanity that the universe operates on scales and times far beyond human experience. Its anomalies suggested that interstellar phenomena could challenge assumptions about matter, energy, and life itself. In this light, observing and reflecting on the object became not only a scientific mission, but a meditation on existence, complexity, and the endless frontier of the unknown. The unfolding story of 3I Atlas generated a profound sense of cosmic awe, reverberating beyond the scientific community into the consciousness of humanity itself. Observers, technicians, and theorists alike were confronted with the majesty of an interstellar traveler that had journeyed unimaginable distances, surviving the cold void of space, and now performing behaviors that defied prediction. Each observation, every reflective glint, rotational shift, and trajectory anomaly served as a reminder that the universe is vast, complex, and capable of exceeding the bounds of human expectation. This awe was not merely emotional, it was intellectual, born of the interplay between observed phenomena and the limits of understanding. Scientists grappled with data streams, simulations, and theoretical models that could partially, but never fully, account for the object's behavior. The incomplete understanding fostered a deep appreciation for the intricacies of interstellar physics, the delicate balance of forces governing matter, and the subtle interactions that could alter trajectories across light years. In this sense, wonder became inseparable from analysis, and observation itself became a meditation on the vastness of possibility. The cosmic scale of the phenomenon amplified its emotional resonance. 3. Atlas's journey had begun long before humans existed, traversing the galaxy with indifference to terrestrial concerns. Its passage near Mars was fleeting yet historically significant, a reminder that humanity's window to observe such events is narrow and precious. The object's behavior, seemingly impossible yet undeniably real, inspired reflection on the limits of perception, the provisional nature of knowledge, and the humility required to confront a universe operating on scales both temporal and spatial, far beyond daily experience. This sense of awe extended to the implications for exploration and discovery. 3. Atlas exemplified the unpredictable richness of the cosmos, emphasizing that even as humanity surveys the heavens with increasingly sophisticated tools, the universe retains the capacity to surprise. Each data point, each anomaly, each unanswered question became a testament to the beauty and complexity of existence itself, reinforcing that scientific inquiry is inseparable from philosophical reflection. The interstellar visitor, in its silent journey, invited humanity to marvel, to question, and to acknowledge the grandeur of the cosmic stage on which all matter, life, and consciousness are set. Even as 3I Atlas receded from Mars, the object left behind a constellation of lingering questions that continued to challenge both scientific and philosophical thought. Its impossible acceleration, unusual rotation, metallic surface anomalies, and magnetic signatures defied full explanation, leaving researchers grappling with incomplete models and partial hypotheses. Every dataset illuminated one aspect of its nature, while simultaneously deepening the mystery in others, demonstrating that even the most thorough observation cannot exhaust the richness of interstellar phenomena. Scientists debated endlessly. How did the object acquire its anomalous properties? Were they the result of unique formation processes in a distant star system, or interactions accumulated over millions of years of interstellar travel? Could unknown natural forces or even exotic quantum effects explain its motion, or did the anomalies hint at phenomena entirely outside human experience? No single answer satisfied all observations, leaving multiple theoretical frameworks viable, each incomplete yet informative. Beyond physics, 3I Atlas prompted broader existential and philosophical questions. Its journey spanned epochs and light years beyond human comprehension, reminding observers of the scale of cosmic time and the fleeting nature of individual perspective. Could there exist other interstellar objects exhibiting similar behaviors, silently traversing the galaxy, unnoticed by humanity? What does the persistence and resilience of such bodies reveal about the conditions and processes of distant star systems? These questions underscored the universe's capacity to surprise and the humility required to confront it. Even after the object departed, its traces remained in the data, in theoretical models, and in the collective consciousness of observers worldwide. Scientists continued monitoring subtle orbital effects, refining simulations, and publishing analyses, ensuring that 3I Atlas's lessons would endure. Its passage became a permanent reminder that the universe contains phenomena at once beautiful, elusive, and inexplicably complex, demanding both careful measurement and philosophical reflection. The lingering questions were not failures of understanding, but invitations to continue exploring, testing, and marveling at the cosmos. As 3I Atlas receded into the depths of space, its influence on the Martian vicinity gradually diminished, leaving behind a trail of scientific intrigue and human contemplation. The sensors that once monitored every fluctuation slowly returned to baseline, the satellites resumed routine observations, and the terrestrial observatories, which had been captivated by the object's impossible behavior, shifted focus to other celestial phenomena. Yet, even in its fading, the object remained a presence in human thought, a reminder of the profound and often unpredictable complexity of the universe. The object's departure was neither violent nor abrupt. It slipped silently along its path, moving away from Mars with the same subtle, precise maneuvers that had defined its approach. Its rotation, magnetic field fluctuations, and reflective metallic patches continued to evolve in ways only partially recorded, leaving scientists with partial datasets that would fuel years of research. This quiet retreat emphasized the ephemeral nature of observation. The opportunity to witness such a phenomenon is brief, contingent upon alignment of technology, timing, and human attention. Philosophically, the fade-out invited reflection on impermanence and cosmic scale. An object capable of traveling light years, surviving interstellar voids, and performing maneuvers deemed impossible now receded, its story written in photons, spectral lines, and gravitational traces. Humanity was left to interpret, model, and wonder, aware that the universe often operates on scales and with subtleties far beyond immediate perception. The silent fade-out became a meditation on curiosity itself, the pursuit of understanding, the patience required in observation, and the humility inherent in acknowledging the limits of knowledge. Though 3I Atlas moved beyond immediate detection, its legacy endured. The collaborative networks, computational models, and theoretical explorations forged in response would inform future encounters with interstellar visitors. Each unanswered question, each lingering anomaly, served as both challenge and inspiration. The universe had offered a fleeting, impossible spectacle, leaving humanity not with closure, but with enduring awe, philosophical contemplation, and the enduring drive to explore what lies beyond. As the light from 3I Atlas faded into the infinite darkness of space, a quiet stillness settled over the instruments, observatories, and minds that had followed it so intently. The rush of data, the hum of calculations, the tense anticipation of every anomaly, all of it gave way to reflection. Humanity had glimpsed a visitor from beyond, a traveler shaped by processes and journeys spanning light years, and now it was gone, leaving only traces in photons, magnetic fields, and memory. The universe, immense and indifferent, had whispered a story, and we had listened. In that stillness, one could feel the profound vastness of cosmic time. While humans live on scales of years and decades, 3I Atlas had been molded over millions, journeying silently across interstellar voids. Its behavior near Mars, so precise, so enigmatic, reminded us that the universe is both beautiful and unknowable, composed of layers of complexity that we are only beginning to perceive. Each anomalous acceleration, each reflective glint, each rotational twist was a note in a symphony beyond immediate comprehension, a testament to the intricate laws and mysteries that govern existence. And yet, there was reassurance in observation, in the tireless work of countless scientists collaborating across borders and disciplines. In every calculation, every spectrum analyzed, humanity had reached toward understanding, proving that curiosity, rigor, and imagination are enduring forces in the face of uncertainty. 3. I Atlas may have been impossible to fully grasp, but its presence inspired growth, reflection, and wonder. As the object receded, we are left not with answers alone, but with the gentle reminder that the cosmos is vast, mysterious, and endlessly inviting. To watch, to measure, to ponder, that is the human way of touching infinity. The interstellar visitor may have departed, yet its story lingers, echoing softly through our minds, urging patience, humility, and the ceaseless pursuit of understanding. Sweet dreams.